We're going to continue using the z-score to find the percentile of a raw score, or vice versa, using the percentile to find the exact raw score. But the raw scores that we're examining are a bit different. Before, they were of a population, or maybe of a sample. Here, we're considering a population with a certain mean and with a certain standard deviation. And then we're fixing a number, a sample size, and we're considering all possible samples of that population of that fixed size. And for each of those samples, we're taking the mean, and we're taking the standard deviation. But in particular with the mean, we're taking the means, and those are going to be the raw scores. So suppose that we were considering all 50-person samples at Salisbury University, and we were considering, I don't know, height. We would take a 50-person sample, find their mean height. Okay, that's a data point. Find another random 50-person sample, find that height, find that average height. That's another data point. All 50-person samples of SU. All of them, we find their mean height. That's all the possible data points in what we call our sampling distribution. That's what, write that clearly. I can't write so well these days, right? Sampling distribution. Okay. Right, that's, again, the distribution where each point is a sample mean of a fixed sample size. The book has a really nice way of showing what's going on here. Consider rolling a 4-sided die. Yes, these dice exist. They're 4 triangular sides. I went ahead and, created all possible rolls, right? What's the mean roll? Like, consider each of these rolls, 1, 2, 3, 4. What's the mean? Well, that's not too bad, right? It's 1 plus 2 plus 3 plus 4. It's 10. Divided by 4. It's 2.5, right? Let's just formalize this, right? Store the result in mean roll mean. The expression is going to be, right, because we just want to be all formal about this, right? So it's the sum of the mean rolls divided by 4. And that should give us 2.5. It sure does. Now we want to find the standard deviation. Okay, so we want to make sure that we're storing that mean roll standard deviation. And remember, for the standard deviation, what we're going to do is we're going to take the square root, right? We learned this trick in Chapter 6. And we're going to find the mean of the roll squared by 4. And then minus the square of the original mean roll. And that should give us the standard deviation, and it sure does, right? Okay, so the mean is 2.5. Again, we should be able to do that just by hand. The standard deviation is about 1.12. Okay, so we're just going to consider that data point, right? Just note that, right? Right, we've got this right here. Circle it, right? There we go. All right, now suppose we roll 2 4-sided dice. All right, we roll, we get a 1 through 4, and then we roll again. What's the mean of each pair of die rolls? And then what's the mean of all of those means? And then what's the standard deviation of all those means? Right, so again, we go to Minitab. I went ahead and drew out all 16 possibilities, right? 16 pairs of rolls. Hope we can see that, right? 4 times 4, right? And then I found the mean roll for each of them, right? Note that it's pretty unlikely to get a mean of 1, right? Just 1 out of 16. It's also pretty unlikely to get a mean of 4, right? Again, 1 out of 16, right? A little less likely than before, okay? But anyway, what's the mean of all of these mean rolls? So let me go ahead and cut this out and just find the mean of these guys, right? And that's not so bad. Just add these up, divide by 16, right? Not 4, 16. Right? Oh, look at that. It's the same as before. I think that makes sense on some kind of an intuitive level, right? We should always expect the mean of each die roll is 2.5, so why would it change if we rolled it twice, right? For the standard deviation, let's make sure that we're storing it in the proper space. And then we're going to go ahead and do that trick, except I will be dividing this by 16. And maybe dividing this by 16. And the standard deviation shrinks a little bit. And maybe that's surprising, but maybe it's a little bit intuitive. Right? Because, as we were saying before, it's less likely to get an extreme value. It's less likely to get a mean roll of 1. It's less likely to get a mean roll of 4. We're seeing more entries in the 2s, 2.5s, maybe 3s, right? Okay, so the data seems to be a little less spread out. Let's just note that. Again, the mean was the same. Standard deviation shrunk a little bit. Okay. Let's just point one thing out super quickly. The original mean was 1.12. What if we divide 1.12 by the square root of 2? We get the standard deviation of what we had before. In fact, let me be a little finer about that. 1.1803. Oh, look at that. We get... That's an interesting relationship, okay? Maybe that's worth jotting down. So we'll say that the standard deviation of our sampling mean, right? The mean of our sampling mean equaled the mean, which was 2.5. The sampling mean, this was equal to mu divided by the square root of 2. Right, which is 1.12 divided by 2. Right, maybe I'll say roughly 1.12, okay. Okay, worth noting. So what do you think will happen if we roll 3 dice? Well, again, I went ahead and I listed them all out in Minitab. And this will be the last time I do that, right? Because there's 64 possibilities, right? Took a little bit of... It wasn't hard work, just a little bit of entry work, right? Those are all the possibilities. All the possibilities you can roll 3 dice and get an outcome, right? 4 times 4 times 4 is 64. Found the mean for each triplet of rolls, right? For example, the mean for rolling a 1, then a 3, then a 3 is 2 1/3, right? Because it's 1 plus 3 plus 3 divided by 3. 7 divided by 3 is 2 1/3. Okay? So what is the mean of all of these mean rolls? All 64 of these mean rolls? Well, I'll let you take a guess, but if you've kind of been following along, then maybe you might guess correctly. You might have a guess. That guess might be, remember, dividing by 64, and sure enough, the answer is, in fact, 2.5, as we expected. What about the mean roll standard deviation? Well, maybe you can think of a pattern there, too. We store that in the proper spot. And we want to make sure that this is being divided by 64. And, look at that, even smaller. And maybe it's even worth noting, let me just put that screenshot over here. I'm just circling that. So again, the mean of the sample mean equals the population mean, which is 2.5. And the standard deviation of the sample mean, well, what was that? Let me just try something really quickly here. We had, let's do this. Whoop, no, we had, just touch it properly. 1.11803, I think it was. That was the original standard deviation. Divided by the square root of 3. Oh, look at that. It gives us exactly the standard deviation that we just got here. That's worth noting. So this winds up being the original standard deviation divided by the square root of 3. And that's about 1.12 over root 3, right? Okay. Okay, interesting. All right, that's the end of this example here. Now, why did I spend so much time on this example? Because I want to show you what's happening, right? As we take a larger and larger sample size, the mean of all of these sample means stays the same, but the variance in standard deviation, the spread, decreases. And if you think about this for a few minutes, I think it should make sense to you. It's less likely to get an extreme value, more likely to get a value closer to the mean. So just to recap, this, the mean of the sample means stays the same, but the standard deviation decreases. Well, I'll actually say that it equals sigma divided by root n, which is to say it decreases, right? As n increases. Yeah, just to be clear, this is also as n increases. All right. Now, for visual confirmation, let's create a histogram of each distribution. This will be super quick, right? All we're doing is we're just creating a histogram. In fact, I think I have them already. Yeah, that was the first one. That's the first histogram, right, of the original, of the original rolls, right? There's an equal chance that we get a 1, 2, 3, and a 4, right? So, no surprise there. Just quickly crop this. Save it. Awesome. This is for the second time, right? We had 16, right? We rolled it. We rolled the die twice. Okay. So you've seen, even though this original distribution was uniform, right? There was an equal chance of rolling a 1, 2, 3, or 4. When we consider the sampling distribution for 2 rolls, that sampling distribution already looks a little more like a normal distribution. And then when we look for the last example, it looks even a little more normal. Right, mind the gaps, so to speak. So if we just post each of these histograms, right, then maybe we can start to see a pattern. Something like that, okay? Maybe just bring these down a little bit. All right. So we consider all possible samples of size n population. The distribution of this is the sampling distribution of of x bar, or I guess you would really just say of size n. Really just what you would say, right? Of size n. Okay. So here's a fact, right? If x bar is the mean of a simple random sample, right? Always of size n. We fixed the size of n, right? We've said, okay, we're going to consider samples of 50 individuals, right? And we know that the population has mean mu and standard deviation sigma. The mean of the sampling distribution is going to be the population mean. The standard deviation, which is also called the standard error, is sigma divided by root n. Right? So for example, now keep in mind the sampling distribution. Simple random sample of size 15, population mu equals 86, sigma equals that. Okay, so just to be clear, so n equals 15. Mu equals 86, and sigma equals 11. All right, so the the sampling mean is the same as mu, which is 86. And the sampling standard deviation, or the standard error, is sigma divided by root 15, which is 11 over root 15. And if we want to calculate that real quick, 11 divided by the square root of 15, what is that equal to? 2.84-ish. Right? Significantly lower than the standard deviation of 11. Okay? Now, the other thing to note is that as we increase the number of die rolls, our distribution, which started off as uniform, right, the mean die roll, became closer and closer to a normal distribution. Even though the outcomes of a single four-sided die roll has a uniform distribution. Let's look at another example. And again, I ripped this right from the book. This is, for the certain make of a car, the number of repairs needed while under warranty has the following distribution, right? So most of the time, while a car is under warranty, let's say its first 3 years, it needs 0 repairs. A quarter of the time, it needs 1 repair. 1/10 of the time, it needs 2. And very small proportions of the times, it needs 3 or 4, right? So this is a clearly skewed right distribution, right? This is a histogram of the frequency table right there, that probability distribution. Okay? But then, what if we consider a sample of 3 cars? And we consider the mean number of repairs for each sample size of 3 cars. Well, then that starts to look like this, right? A little less skewed. Still skewed, but a little less skewed. What about we consider all possible samples of size 10? This is what we get. And then we consider samples of size 30. Look at that. It's practically a normal distribution. So even in the case where we started off with a right skewed distribution, as we increase the sample size, the sampling distribution still approaches a normal distribution as n increases. So then, of course, you could say, well, does this happen with every distribution? And the answer is yes. No, we will not prove this here. Take math stats if you'd like. This is called the central, well, I don't know if I should say the. Yeah, I guess I should. The Central Limit Theorem. X bars, the mean of a large simple random sample. Again, random is very important. And by large, we mean n is greater than 30. Population we know has mean mu and standard deviation sigma. The distribution of x bar is approximately normal with mean mu x bar equal mu, and standard deviation x bar equals sigma. Okay? Oh, sorry, that is not correct. Sigma over root n. All right? So the nice thing, when we have a large sample size, then no matter what, our sampling distribution will be approximately normal. If we don't have a large sample size, we still know that the mean approaches mu, the standard deviation approaches, well, actually, I guess, if we don't have a large sample size, then we're not quite so sure. However, if the distribution is normal, then we always know that it's going to be mu, and it's always going to be sigma. Yeah, so it's going to be that. So let's take a look. For example, 6, right? Number 26. What do we have here? So, mean monthly rent is $2,631. Standard deviation is a nice even $500. We sample 100 apartments, so n equals 100. Okay, so let's look at part A. What's the probability that the sample mean rent is greater than 2,700? So let's just get a chart going. Let's see. I guess we should note quickly that n is 100, which is greater than 30. So I guess I could just say, to be clear, mu, right, our mean of the sampling distribution equals the mean of the population, which is 2631, and sigma x equals sigma over root n, which equals 500 divided by the square root of 100, which is kind of nice because it's 500 divided by 10, which is 50. So we've got a chart that looks kind of like this. This is a sampling distribution, right? So our mu is still 2631. We go out one standard deviation, we subtract 50. So we have like 25, 81, I guess, is that? And then this is 2681. Dollar signs, right? Right there, okay. All right, so we got that, okay? Just a rough idea. This is the sampling distribution. Okay, so what's the probability that sample mean rent is greater than 2,700? Well, it looks relatively small. Right, relatively small. So I guess we'll say the probability that x bar is greater than 2,700 is going to equal, well, we're just going to use Minitab for this, right? Well, get out of here. Get out of here. So remember how we do this calc, probability distribution. Wait, no, sorry. I lied. Graph, probability distribution plot, view probability. Distribution is normal, sure. The mean, we know, is 2631. Standard deviation is not 500, it's 50. Okay? Now we want to make sure we're right-tailed, specified x value, and that x value is 2,700. Okay? And so it looks like it's 0.084, right? All right, so let me just quickly take a screenshot. I'll do this just for the first part. For the other ones, I won't bother with the screenshots. Just want to have some piece of evidence for how we did this, okay? All right, so again, as I was saying, pretty unlikely. For part B, more of the same, right? Let's see what we're doing for part B. Probability that it's between 2,500 and 2,600. Now, it doesn't matter whether we're equal to or not equal to. These are the real numbers. So, probability of equaling a single point is 0, so it doesn't matter whether it's less than or equal to. Graph, probability distribution plot, same thing as before, but we're doing the middle. And so I guess we're doing 2,500, and then this is 2,600. I think that should give it to us. All right, so we get that, 0.2632. All right, so another couple of examples. Find the 60th percentile of the sample mean. Again, we just use Minitab, right? Graph, probability distribution plot, view probability. Options, here we want a specified probability, 60th percentile. Percentile means we're always doing left tail. Okay. It looks like it's 2644. 60th percentiles, right there. Pretty close to the 50th, right? What makes sense, though, when the standard deviation is only 50, right? Again, that makes sense. For a sample of 50 houses, they shouldn't be deviating too far from the mean, right? All right, let's see. Can you tell whether it'd be unusual if the sample mean were greater than 2,800? Goodness gracious. Well, the probability that the sample mean is strictly greater, or greater than or equal to, doesn't matter. 2,800, it's going to be very small. So the answer is yes. Right, again, graph. Oh, no, I guess specified x value right tail. We're doing 2,800, so the answer is going to be a clear yes. Look at that, 0.00036. The answer is yes. Oh my goodness. Definitely unusual. All right, and then last but not least, do you think it'd be unusual for an individual apartment to have rent greater than 2,800? Now here, they're asking about the word individual. Well, I really wanted to do this guy. Okay. Well, for an individual let me just write that. For an individual apartment, we have mu equals 2631, but here's the difference. Sigma equals $500, not 50, because it's a single apartment, and for the population, standard deviation is 500. So, we go back to Minitab. Graph, probability distribution, probability. Oh, let's make that 500. Now if we do it out, that's not so unusual. So I guess I'll just say P of x, not x bar. P of x greater than 2,800 equals 0.3677. Not so unusual. Right? It would just be weird if 50 of them average to have a mean rent of more than 2,800. All right, last but not least, a couple of examples. This will be quick, don't worry. 500-page book contains 250 sheets of paper. Thickness has a mean of 0.08, standard deviation 0.01. Someone wants to know that a randomly chosen page, singular, is more than 0.1 meters. Is there enough information to compute the probability? And the answer is no, because we don't know that the thickness distribution is normal. Right? They never said that the page thickness was normally distributed. So we don't know that we get to do all this z-score, z-chart, probability distribution plot stuff. Okay? If it were a sampling distribution, we consider it a sample of, 30 pages or 31 pages, then the answer is yes, because the sampling distribution is normal no matter what. For a sufficiently large sample, right? All right, let's look at 32, right? Apples in bags weighing 10 pounds, sample of 50 bags, had a mean weight of 10.3 pounds, standard deviation of 0.1 pound. Someone wants to know the probability that a randomly chosen bag, again, singular, weighs more than 10 pounds. Again, no, because we don't know the bag weight is normally distributed. Again, if they said a randomly chosen set of 50 bags, right, that would be different. They just said a single randomly chosen bag. So that's all I've got.